Hello, I'm St. Jordan, and I will be presenting Lab 4 for Physics 2212 Circuits. The purpose of this lab is to observe the conservation of energy within a circuit, and the main principles used in this lab are the ideas of conservation of energy, Kirchhoff's law, and Ohm's law. The objective of this experiment are to predict the behavior of a given circuit, measure the currents and potential differences within the circuits, and examine the behaviors of the circuit with resistors and capacitors. We will be doing this through a PHYS simulation, and we will denote the circuits as the system and everything else as the surroundings. For part 1, we have a circuit with two 1.5 volt batteries, two resistors with 47 and 100 ohms, and an ammeter. We see that the ammeter reading of 0.02 amps is the current reading of the circuit, which can be calculated by dividing the potential difference with the resistance shown here in the equation. Next, we take the voltmeter to read the potential difference from location to location shown in the picture. You can pause here to see the reading for each respective location. We see that the loop rule applies with the circuit, with the ending voltage being 0 due to the resistors. Here's a visual graph of what is occurring as the current flows through the circuit, with both batteries adding voltage and the resistors subtracting voltage. By connecting another ammeter parallel to the 100 ohm resistor, we see that the readings have increased to 0.06, meaning that there is less current flowing within the resistors, causing an increase in current flow. You can calculate the resistances for each location shown in each equation, with the increase in voltage seen on the side. For part 2, we create two new circuits with one 9-volt battery each, two separate light bulbs of 10 and 20 ohms, and a capacitor. To charge a capacitor, you must first complete the circuit shown in the top picture until the light fully dims off. To discharge the capacitor, you must take away the battery and then connect the loose wires shown in the bottom picture, and you will see the light also go bright and then dim once again. We can see that the times at which it took to charge and discharge both bulbs are at the bottom, and you can pause them to see them in greater detail. In part 3, we have a new circuit with a 30 ohm bulb, 9-volt battery, and a 0.2 farad capacitor. The goal here is to track the rate at which this capacitor discharges per second. We can do this by first charging the circuit until the voltmeter reads 9 volts, pausing the simulation, and removing the battery to complete the wires. While still paused, we can turn on the timer, and every time you unpause the simulation, we can pause it again for each repetitive second to get the voltage reading. This will then be linearized by taking the natural log of the voltage reading and then dividing that by the initial voltage of 9 volts. You can pause here to see the data in greater detail. After putting into the graph, we get the following linearization and values. We can relate the slope of the line to the negative inverse of RC, which is the resistance times the capacitor reading. And based off of that, it should be around 6 seconds. And from the values gathered, it got to 6.017 seconds, which is essentially the same thing, and is very negligible. Errors could have been from human error when doing the readings per second. Now, what if we did this with a real ammeter? Well, the readings would be slightly less because the ammeter does provide some resistance in a real life setting and not exactly 0 like it is in simulation. And what if we used a real battery with no resistance? How quickly would it take to charge a capacitor? Well, if there was no resistance involved, then it would essentially be much faster than if it were to have resistance. Like in the simulation we're doing, part 3, it is very fast compared to having a resistor. And that's the end of this presentation. Thank you for listening.